Aloha class. In this lesson, we're going to be talking about stacks. Particularly, we're going to be talking about stacks as implemented through linked lists. So let's go ahead and take look at our text here. So when you're thinking about stacks, think of it like a stack of books or a stack of plates. So you've got you take one, you put it down. You take another one, you put it on top of it. So the first one in will be the last one out. So when we think of when we had queues, queues were the first one in, first one out. This one is the opposite. The first one in is going to be the last one out. So FILO, FILO, first in, last out. Last in, first out, LIFO. So anyway, the way we describe it here, if you look at this, we've got the way you implement a stack is you have a pointer that points towards the top of the stack itself. So you're pointing to the top of the stack. The stack is pointing to a node essentially, and the node has a data piece and it has a link that links to the next one down. And then the next one down, that node has data and a link to the next one down, all the way until you get to the last one. In other words, the first one that was entered into the stack. Once you get to the first one entered in the stack, it has the data, but the next pointer points to null. So that's the basic premise here. So now let's go ahead and take a look. We're going to have a participation activity first. So referring to the figure up here, the stack has 3 items. Is that true? Looks like it to me. A pop operation would return 56. 56 is the one at the top, so that looks to be true. Then instead of top pointer, numstack could have a bottom pointer that points to this one. Well, it could have, but if we point to here, there's one little problem. These are one-way pointers. They don't go up as well. You can have a doubly linked stack, but this isn't what we're talking about. We're talking about a singly linked stack. So because we've only got one pointer in each one, they're only pointing down. So if we put a bottom pointer here, we're only ever going to be able to access this one right here. So that's why that would not work. So yeah. So because the next one is inaccessible. So we'd have to reverse the whole thing or something like that if we wanted to use a bottom pointer. So push and pop operations. So we've got the concept of adding and removing here. So pushing, when you push onto the stack, you're going to be creating a new list node. You're going to take it, you're going to put your data into the node, and then you're going to take the link, you're going to link it to what was the old top stack. And then you're going to take the top of the stack pointer and you're going to point it now to this new node. So there's several different operations that go on here. And in the old days, we used to implement this in C, and it was a pain in the. Never mind. Anyhow, let's go ahead and go through this and take a look at it. One other thing to note is that a pop is performed by assigning a local variable with the top node's data. Then you're going to remove the list's top node. So you pull that one off. Then you're going to return the local variable. What it doesn't mention there is it's also going to reassign the pointer, the top pointer. So it does that in the code here. So let's go ahead and watch what happens. So let's take a brief look at the code. So we've got stack push. So this is taking the stack and we're taking item. So we're going to say new node. We're going to allocate new linked list node. That just means we're going to be making a node here. Then we're going to go ahead and we're going to assign the data to whatever item we passed in. And then the next link is going to be the top stack. And then the new stack top is going to point to ourselves, so to this new node that we just created. Okay. And then stack pop, essentially given a stack, you're going to say popped item equals the data in that top node. You're going to say that the top is now assigned to the top's next one, which would be, pointing to the one right after it. And then you would return the popped item. So that's how it generally works. Then in the main section here, you're doing a stack push of 45, then 56, then 11. Then you're going to say pop value equals stack pop stack. So when you push in stack, when you push in everything in this order, 45 is on the bottom, then 56, then 11. So 11 will be popped off. So let's go ahead and run this. So first, pushing 45 begins by allocating a new node. The node's data is assigned with 45, and next is assigned with the stack's top, which is null. So this is for when we have just a single item. There's no next one, so it's null. So now, when we go to the next statement, which is stack push stack 54, or 56, pardon. So when we do that, then we assign the next pointer with the stack's current top node, node 45. So we take, we essentially, have next pointing to the what was top was pointing to before. Then the stack's top is reassigned with the new node. So we're going to reassign that to point to the one we just created. Now 11 is similarly pushed onto the stack. So we go ahead, create the node, readjust our top and everything, point our next down to the next one. And then a pop assigns a local variable with the top's node data, removes the top node, and returns the local variable. And notice how it shifts down here and top is now pointing to the next one down. So it followed the next link to get to this one. And it returns the pop value. So that's how popping works, and pushing as well, as we saw first. So pushing and popping. So we get down here and we have some questions. So a push operation changes the what? So when we push it down, it's going to change. Is it the stack's top node pointer? Yeah. Data value of the stack's top node. It does not change that because it's going to be putting a new one up there. And then does it change the next pointer of the stack's top node? No, because it's already pointing to the next one down the list. So I'll let you do the other ones here. And then we have challenge activity. Challenge activity, given an empty stack, num stack, what does the top node pointer point to? If the pointer is null, enter null. So then we look at this example 5 or null. After the operations, which node does the top node point to? Stack push. So we've got 66, 58, 92, and then here. So let's go ahead and start. So what does the top node pointer point to? So if we're pushing these, we push this on. This is going to be the bottom, one up from the bottom, and then the top. So the top is going to be pointing to this. So it's going to be pointing to 95. And then, after the operations, which node does the top, given an empty stack, what does the top pointer to? So it's going to be null, sorry. And then after everything, it should be pointing at the last added one, which is 92, because that'll be the top. So let's go ahead and see if that's correct. Yep, so we're good. So go ahead and use your knowledge of how these stacks work. Remember, stacks are going to be first in, last out. So just go ahead and answer the other two. And that's it. So this is a pretty quick section on stacks using linked lists. So we've been doing this type of thing for a long time. I remember 35 years ago still using this and implementing it in a different language. So this is one of those data structures that's been around forever. So anyway, if you have any questions, feel free to reach out, send me an email. We'll set up a Zoom. Otherwise, I'll see you in the next video. Aloha.